On this next problem, we have another binomial squared. So like we said, we have to write that out twice. And then I'm going to distribute. The 5 is going to multiply to both terms. So 5 times 5 is 25. 5 times the square root of 3. Now remember, the 5 is on the outside of the radical, but the x plus 3 is on the inside. So we're just going to get 5 times the square root of x plus 3. Then I'm going to come back and grab that plus root x plus 3 and distribute him to both sides. So then I get plus 5 times the square root of x plus 3. And then the square root of x plus 3 times itself, the square root of x plus 3, is the square root of x plus 3 quantity squared. And let's reduce if we can. The first term is 25. That doesn't have anything to reduce, nor does it have any like terms. The two middle terms, 5 times the square root of x plus 3 and 5 times the square root of x plus 3, both of the x plus 3 underneath the radical is exactly the same, which means I can add their coefficients to get 10, and the radicands stay the same. And in our last term, the square and the square root undo each other, and I'm just left with x plus 3. Now, a lot of students would assume that you're done at that point, but now that the x plus 3 is out of the radical, now the 3 and the 25 are like terms, so we have to add them to get 28 plus 10 times the square root of x plus 3 plus x. This is my final answer. On the next problem, we have another binomial squared, so let's write that out twice. So the 2 needs to multiply to both. That gets me 4 minus 2 times 3 is both on the outside, the coefficients, times 5, the square root of 5x minus 1. Then I'm going to come back and grab the whole second term. Negative 3 times positive 2, that's negative 6 times the square root of 5x minus 1. And then the last term, I have negative 3 times negative 3, that's positive 9. The square root of 5x minus 1 times the square root of 5x minus 1 is the square root of 5x minus 1 quantity squared. In the red, it doesn't look like 4 can reduce at all. In the two middle terms, there's nothing to be reduced here, but because they are like terms, I can add or subtract their coefficients. In this case, negative 6 plus negative 6 is negative 12. But the radical stays the same. And then on the last green term, I have 9 times the square root and the square undo each other, and I'm just left with 5x minus 1 out of the radical. Now I can distribute and get 45x minus 9, and all the other terms are going to stay the same. So before I say I am done, is there anything else that is like terms that I can still add together? Well, yes, there is. The 4 and then minus 9 are now both out of radicals, and now they can add. So 4 minus 9 is negative 5. And then we still have minus 12 times the square root of 5x minus 1 plus 45x. And now there is nothing else that can combine, and I am done. Now on this third problem, we don't have any squared, which is great. It's just a binomial times a binomial. So I'm going to distribute the red. Root 3 times root 3 is root 9. Root 3 times positive root 2 is positive root 6. And then I'm going to go back and grab the negative times the square root of 2 and distribute that as well. Negative root 2 times root 3 is negative root 6. Negative root 2 times positive root 2 is negative root 4. I'm going to try to reduce what I can. The square root of 9 is 3. The two middle terms are like terms, and they can add together. Root 6 minus root 6 adds to 0. Well, that's kind of cool. And then the green, minus times the square root of 4. The square root of 4 is just 2. So when I subtract these, 3 minus 2, I'm just getting an answer of 1. Wow, that's pretty cool. I had a radical binomial times another radical binomial, but I came out to have just a whole number as an answer. That was pretty cool. So the next thing we're going to talk about is conjugate pairs. Notice that in the last example, when we took the square root of 3 minus 2 times the square root of 3 plus 2, the solution was an integer answer 1 with no radicals. Now, this occurred because the square root of 3 minus 2 and the square root of 3 plus 2 are conjugate pairs. Let me show you that it truly does work. I'll do 2 more examples for you so you can see that these conjugate pairs do come out without radicals. So the square root of x plus 5 and the square root of x minus 5 are conjugate pairs, and we'll talk about why they are in a minute. But for now, I just want to show you that they truly do come out to whole numbers. Root x times root x is the root x squared. Root x times minus 5 is minus 5 root x. Then I'm going to take my 5 and distribute that as well to get plus 5 root x minus 25. Okay, notice that the two middle terms add to 0. The first term, the square and the square root, undo each other and you're just left with x minus 25. The problem started off with radicals, but it ended with no radicals. On the next problem, I'm going to distribute my first term. Radical 3 times radical 3 is radical 9. Root 3 times root 5 is root 15. I'm going to grab my 5 and distribute that as well. That gets me plus root 15 minus root 25. The square root of 9 is 3. The two middle terms add to 0. And then the last one we have minus the square root of 25 is just 5. When I add these two together, I'm just getting negative 2. Notice that my original problem had radicals in it, but my answer had no radicals in them. All of these binomials are conjugate pairs of each other. A conjugate pair is found by changing the middle term of a binomial. So the conjugate pair of the square root of 3x plus 7 is merely the square root of 3x minus 7. The conjugate of the square root of 2 minus 5 is the square root of 2 plus 5. Notice it's just the sign between the two terms that changes. The sign of the first term stays the same. When conjugate pairs are multiplied, we can easily get the result by using the difference of squares formula. So if I distribute this out, that gets me a squared minus ab plus ab minus b squared. Notice that the two middle terms add to 0 and go away. And what do I have left at the end? Just a squared minus b squared. Now, because these are squared, they are going to undo a square root if we had a square root in our conjugate pair. So that's why these conjugate pairs, when you multiply them, come out to be expressions with no square roots in them. So what we could do instead of multiplying this out, now you could obviously take the 3x and multiply it just like we have been, but I'm trying to show you that there is a shortcut here. So I know that this is a conjugate pair because the terms are exactly the same, but the sign in the middle is the opposite. So I know that they're conjugate pairs. And the difference of squares formula says that this is going to multiply into a squared minus b squared. Well, my a is the root 3x, and the b is the 7. So if I just evaluate this, the square and the square root undo each other, and I'm just left with 3x minus 7 squared is 49. This is the solution to the binomial product. And I didn't really have to do all that foiling. It's a whole lot faster if you use the difference of squares formula. But if you want to do it the way we've been doing it on the previous two examples, by distributing it, it will still work. You're still going to get the same answer. So on this next problem, let's practice our difference of squares formula. We know that because the first binomial and the second binomial have the same terms but are opposite signs, it's a conjugate pair. So I'm going to use my difference of squares formula that says I have the first term a squared, which is root 2 squared, minus, because that's what the formula says, minus the square root of 5 squared, or b squared. So I have the square and the square root undoing each other, which gets me 2. And then the square and the square root undoing each other, which gets me 5. And my final answer is -3.